Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 3 on Fractional Exponents Revisited. Because let's be honest, we've done some work with fractional exponents already in this unit. We've already done it previously in this course. So let's jump in and do quite a bit of review on fractional exponents. These things are quite important. Fractional exponents and roots. It's very important to understand the connection between radicals, also known as roots, and fractional exponents. We've seen this in our lesson with square root and cubed root functions. So let's review the most basic fractional exponent, exponents that are unit fractions. If n is any positive integer, then we define a unit fraction exponent as b raised to the 1 over n is equal to the nth root of b. All right, and remember we kind of rationalized that these things were equal to each other by saying if we raised both sides of this expression to the nth power, then both of them would be equal to b, right? So they are equivalent. Now, there's a lot of different things we want to be able to do with that. Let's take a look at exercise number 1. Rewrite each expression in the form a times x to the b, where a and b are both rational numbers. All right, well in some cases this is very easy. Like letter A, we have 5 times the square root of x. So all I'm asking you to do in a situation like that is just be able to rewrite this as 5 times x to the 1/2. That's all. Now something like letter B is a little bit trickier. Let's take a look at that. Here we have the 5th root of x divided by 4. Now I want this written as a number times x raised to another number. So the first thing I would note in this is that this is equal to 1/4 times the 5th root of x, right? Dividing by 4 is the same as multiplying by 1/4. But then I can write the 5th root of x as x to the 1/5. So I can rewrite all of that as 1/4 times x to the 1/5. This type of manipulation is very important, especially if you're going to go on and take courses in pre-calculus and calculus, so we want to get a little bit of work with it in Algebra 2. All right, I'd like you to pause the video and see if you can do both letter C and letter D. Take a shot at it. All right, well, letter C, right, I can think about this to begin as 7 times 1 over the cubed root of x. Boy, that looked awfully messy. 1 over the cubed root of x. I can then rewrite that as 7 times 1 over x to the 1/3, and then I can write that as 7 times x to the negative 1/3. All right. Now, some of you could probably very easily go from here down to here without writing out these two steps. I just want to make sure that everyone understands how I go from here to here. And really, I'm just kind of using fraction properties of just normal fractions, in addition to this whole idea of fractional exponents and corresponding roots. So letter D, here I have 5 divided by 3 times the 10th root of x. Very, very similar to letter C. The first thing I might do is think about this as 5/3 times 1 over the 10th root of x. Then I might think about this as 5/3 times 1 over x to the 1/10, and then eventually 5/3 times x to the negative 1/10. All right, there we have it. Simple enough, all right? And we probably could have done manipulations like this long before this lesson, but we kind of want to get more practice with fractional exponents and how they correspond to roots. Let's take a look at a more complicated expression. Now, more complex fractional exponents. We can then extend this notion, what we were just looking at, to include fractional exponents that are not unit fractions. And unit fractions are 1/2, 1/3, 1/5, 1/10, etc. We do this by utilizing the product rule of exponents. So let's make sure we really kind of understand this. General fractional exponents. For the positive, important, positive rational number m divided by n, b raised to the m divided by n is equivalent to b to the m raised to the 1/nth, 1 over n, that is, not to the 1/nth, I don't know what that would be, which is the nth root of b to the m, right? Or b to the m over n is equal to b to the 1 over n, then raised to the m, which is the nth root of b raised to the m. So this is very important, okay? So before we kind of move on, I always have students that are kind of like, oh, when they have a fractional exponent, they can't really remember whether the numerator is the root or the denominator is the root or whatever, and yet they don't seem to have any kind of problems with things like this, right? So it's really key to understanding something. If you have a number, a fraction, like this, it can be thought of as this, or it can be thought of as this, right? So m over n can be thought of as m times 1 over n, or 1 over n times m. And the reason that that's important is then when I've got something like, b to the m over n, I can think of that as either b to the m that's then been raised to the 1 over n, or I can think about it as b to the 1 over n that's then been raised to the m, right? And now it's very clear to me that the denominator represents the root and the numerator represents the sort of normal multiplicative power that it always has. All right, let's take a look at exercise number 2. Rewrite each of the following power/root combinations as a rational exponent in simplest form. All right, cool. So in letter A, I've got the square root of x to the 7th. All right, so we're not trying to simplify anything here particularly, even though it says in simplest form. We just want the rational exponent in simplest form. So what I know in letter A is I can rewrite this as x to the 7th raised to the 1/2. But then I have this product property of exponents that tells me I can multiply the two exponents, and I simply get x to the 7/2. That's simple. Let's take a look at letter B. Here I have the 4th root of x to the 6th. That's simple enough. I can rewrite that as being x to the 6th raised to the 1/4, which is then x raised to the 6/4, and I can simplify 6/4 into 3/2. So I can rewrite the 4th root of x to the 6th as x to the 3/2. Okay, what I'd like you to do is pause the video for a moment and try to do letter C and letter D. All right, in letter C I have the square root of x raised to the 6th, so I can rewrite that as x to the 1/2 raised to the 6th, and then that's going to be, well, actually, that's just x to the 3rd, right? 1/2 times 6 is 3. Letter D, very similar, except it doesn't simplify nearly as nicely. I have x to the 1/3 raised to the 10th, and that's just going to be x to the 10/3. Now we'll see further ways of how we can simplify these in the future, but for right now I just want you to be able to do that. Okay, let's keep going. Exercise number 3. If f of x equals 10 times x to the 3/2 minus 24 times x to the -1st, then which of the following represents the value of f of 4? Find the value without the use of your calculator. Show the steps in your calculation. Yet again, I'd like to remind you that of course you could do this problem with your calculator very easily, right? But I want you to be able to do it without your calculator so that you understand both what a fractional exponent is and what a negative exponent is. So pause the video now and see if you can figure out which of those 4 choices represents the value of f of 4. All right, let's do it. So we've got f of 4 equals 10 times 4 to the 3/2 minus 24 times 4 to the -1st. Awesome. Well, let's now interpret, right, 4 to the 3/2. 4 to the 3/2 is going to be 4 to the 1/2 raised to the 3rd. And now let's interpret 4 to the minus 1 as 1 over 4 to the first. Okay, well, keeping on going, right? 4 to the 1/2 is the same as the square root of 4, raised to the third. Of course, 24 times 1/4 is 6. That's just 24 divided by 4. And now we have 10 times 2 cubed minus 6, right? 2 cubed is 8, so we'll have 10 times 8 minus 6. That's going to be 80 minus 6, and that is going to be 74. And yes, I agree with you, whoever you are, that would have taken me probably about 10 seconds on my calculator. But it would have also meant that I probably didn't understand what a fraction of 3/2 was, or sorry, what an exponent of 3/2 was, or an exponent of -1. So make sure to be doing as many of these as possible without your calculator. Trust me when I say, look, I'm not going to give you something where you're trying to figure out what, 2,156 is to the -3/8, right? That's not the point in this kind of problem. This kind of problem is really to try to get us to understand those exponents better. Let's take a look at exercise number 4. Which of the following is not equivalent to x to the -7/3? All right, well, I'd like you to play around with each of these choices and see if you can figure out only one of them is not equivalent to x to the -7/3. See if you can figure out which one it is. Well, watch as I produce all 3 that it is equivalent to. The first thing I might note when I have x to the -7/3 is by the definition of a negative exponent, this is the same as 1 over x to the 7/3. All right, so one of them that it is equivalent to is choice 1. Right, so I'm going to mark that out because I'm looking for the one that it's not equivalent to. Now, let's kind of take a look at this, right? This one can be thought of, right, as 1 over x to the 7th to the 1/3, which is 1 over the cubed root of x to the 7th, right? And that is this one. So I'm going to mark that one out. Okay, one more of them, right? I can take a look at this, and I can think about this thing as equal to x to the -7th to the 1/3, right? But that's 1 over x to the 7th to the 1/3, and that's the cubed root of 1 over x to the 7th. All right, and that's this one. So that one's out, right? It's only this one that I can't produce, and in fact, let's kind of take a look at that one, right? That's 1 over the 7th root of x to the 3rd, but that would be 1 over x to the 3rd raised to the 1/7, which would be 1 over x to the 3/7, right? But I'm dealing with x to the 7/3, and in fact, going all the way, right, I could then look at this as being x to the -3/7. So in that last choice, the one that's not equivalent, right, it's that whole root power thing that has been reversed. Right? Here, ultimately, I have a 3rd root and a 7th power. Sorry, it's a little bit hard to see that. A 3rd root and a 7th power, whereas in choice 2, I've got a 7th root and a 3rd power. All right, so ironically, the one that is correct is the one that's incorrect. And anyway, however you take that, you've done problems like this before. Okay. So now let's talk about, quote, simplifying roots. All right, fractional exponents play by the same rules, i.e. properties, that all other exponents do, okay? It is these properties that can justify many standard manipulations with square roots and other types of roots. For example, simplifying roots. Now, you saw simplifying roots back in Algebra 1, and I put simplifying in quotes because I don't truly believe that a square root is simplified or a cubed root is simplified when we do this. But It is a skill that they want you to know in general in the standards. So we're going to take a look at it and try to understand why we can do what we're going to do. So let's take a look at exercise number 5. We only consider a square root, quote, simplified, unquote, when all its perfect square factors have had their square roots evaluated. All right, so let's work up to this. Letter A. Fill in the exponent property below, AB raised to the nth power. All right, now, what does it mean? If I have a product raised to a power, a product, not a sum, not a difference, but a product raised to a power. So like if I had something like a times b to the second, right, that would be ab times ab, and that would be a to the second, b to the second. All right, so there's this power, or this exponent property that says if I've got a times b raised to the nth, that's the same as a to the nth times b to the nth. It's one of the, random exponent properties that is useful, but we don't use it a ton. But there it is, right? Now let's take a look at letter B. Rewrite the square root of 28 in factored form, with one factor being the largest perfect square divisor of 28. Also write the square root in exponent form. All right, so I want to write this thing down in factored form with one of the two factors being the largest perfect square that divides into 28. Now keep in mind, right, the perfect squares are 4, 1, 4, 9, 16, 25, 36, etc. You want to think about perfect squares as being nice numbers, right, to take the square root of. Now the biggest one of these that divides into 28 happens to be the number 4, right? So I can write the square root of 28 as being the square root of 4 times 7. All right. Now it said also write the square root in exponent form. So in other words, I can say all of this is equal to 4 times 7 to the 1/2. Okay, great. So now let's take a look at letter C. Simplify the square root of 28 using B and the property from A. In other words, right, I can look at the square root of 28 and think of it as the square root of 4 times 7. But since the square root is an exponent, this property must hold, which means, right, that the square root of 28, which is the equivalent of 4 times 7 to the 1/2, can be thought of as 4 to the 1/2 times 7 to the 1/2. But that's then the same as the square root of 4 times the square root of 7. Now there's nothing I can do with the square root of 7, but I can make the square root of 4 into 2. So we say that the square root of 28 is now simplified into 2 times the square root of 7. Now you might disagree that this is a simpler form than this, but that is technically what it means to simplify a square root. Now we can generalize this in letter D. Let's take a look. The square root of a times b equals, and the nth root of a times b equals. Now this doesn't have to even, a and b don't have to be perfect squares or perfect cubes or anything. The plain fact is, if I've got a product underneath the square root, then I can just say this is the square root of a times the square root of b. And I can say more generally that this is the nth root of a times the nth root of b. Because all I'm really doing is using that exponent property from part A, which is if I have a product, right? If I have a product raised to an exponent, whether that exponent is fractional or whole number or negative or anything else, then I can apply that exponent to each part of the product. Okay, so let's do some simplifying of square roots. Exercise number 6. Simplify each of the following square roots. Show the manipulations that lead to your answers. All right, so let's take a look at letter A. Now you did this quite a bit in Algebra 1. The biggest difference is that you probably didn't have variables underneath the square root. Now, I just want to think about this for a second. First, I'm going to take a look at 18, right? And I'm going to think to myself, well, what's the biggest perfect square that divides into 18? And that's 9, right? So, right, 18 is equal to 9 times 2. It's also equal to 3 times 6, right? But neither 3 nor 6 is a perfect square. So I really need that 9 getting in there. Now the other thing I'd like to note, right, is that x squared times x squared is equal to x to the 4th. Not because 2 squared is equal to 4, but because 2 plus 2 is equal to 4, right? So when we multiply two things that have the same base, we add their exponents. We don't multiply them. Unfortunately, 2 plus 2 and 2 times 2 are the same number. But be very clear, this is equal to 4 because we add the exponents. So I can take this entire thing, and remember what I'm looking to do is I'm looking to take the square root of everything I can and leave everything I can't. So I'm going to break this down into this, right? Then I'm going to make it into this. All right, so I'm going to break it down into the square root of 9x to the 4th times the square root of 2. Now I can take the square root of each of these. The square root of 9 is 3. The square root of x to the 4th is x squared. And I can't do anything with the square root of 2, so I'm just going to leave it. So 3x squared times the square root of 2. All right, let's do another one. Let's take a look at letter B. The square root of 200 times x to the 5th times y to the 3rd. All right, let me write this a little bit bigger as usual, just so that you can see it. Okay. Now again, the numerical part probably isn't too bad, right? You're thinking to yourself, all right, 200, right? We're all dealing with square roots here. So again, perfect squares. I won't even write the 1 down, but we have 4, 9, whoops, I skipped right over 16, 16, 25, 36, 49, 64, 81, 100, 121, etc. Okay? I'm thinking about the biggest one of these that divides into the number 200. I want the biggest one that divides into 200. Should be pretty obvious. It's 100. Okay. So I'm going to break this into 100. Okay. Now, what about the variables? That's a little bit trickier. But keep in mind that I can easily take the square root of x to the 4th. It's x squared. So I'll put in x to the 4th here. I can also easily take the square root of y squared. It's just equal to y. So I'm going to put a y here. And now all of that would have to be times 2, x to the 1st, y to the 1st. So I can factor what's underneath there. Whoops, made a mistake there. Sorry about that. That should have a squared on it. All right, 100, right? Its square root's nice. It's going to be 10. X to the 4th, its square root is nice. It's going to be x to the 2nd. And the square root of y squared, you don't get any nicer than that. That's just going to be y to the 1st. So now I can break this into the square root of 100 x to the 4th, y to the 2nd, times the square root of 2xy. And what I'll eventually have is then just 10 times x squared, y to the 1st, times the square root of 2xy. I take the square root of what I can, and I leave what I can't. Now, one thing that you might have kind of figured out is that when you're looking at variables, you can take the square root nicely of anything that's raised to an even power. And that makes a lot of sense because remember, square roots are the 1/2 power and you're multiplying those two powers together. So it's like, well, if I multiply a power of 4 times a power of 1/2, I get a power of 2. If I multiply a power of 2 by a power of 1/2, I have a power of 1. So it's very easy to take the square root of anything that has a power that is even, right? Because I'm just really dividing by 2. Let's take a look at letter C. Here I have the square root of 147, x to the 9th, y to the 4th. Okay, what I'd like you to do is pause the video now. I want you to look at the 147. I want you to think about the x to the 9th. I want you to think about the y to the 4th. Start with the 147. You might want to use your calculator to think about which one of these numbers is the largest one that goes into 147. So start there, okay? And if you have to, take your calculator out. 147 divided by 4, divided by 9, divided by 16, divided by 25, etc. See if you can figure that out and then tackle the variables as well. Pause the video now and think about that for a moment. All right, so, now that you've thought about it a little bit, you've probably figured out what number goes into 147. But if you didn't, right, what you want to do at this point, because sometimes it can be tricky, is you want to just take the calculator out. Now, you're looking at 147, so there's no way it's an even one, right? It can't be either 4 or 16 or 36. So maybe I'm thinking about, is 9 the biggest one? So I check it out, and no, 9 doesn't go in there nicely. It's not going to be 25 either, because if it were 25, then it would be like a 145 or 165 or something like that. Let me see about the 49, see what happens there. There it is, right? So 49 divides into 147 3 times. Now, what I like starting to do in these problems is sort of skipping the absolute first step, and I start to just write down 2 square roots. And I'm going to collect everything I can take the square root of over here. And then I'm going to, let me go back into full screen. Then I'm going to collect everything else that I can't take the square root of over here. So remember, 147 was 49 times 3. Okay. Now, x to the 9th. It would be so tempting to think, oh, x to the 9th. That's going to be just, square root's going to be x cubed. Keep in mind that x cubed times x cubed is x to the 6th. And it's actually x to the 8th that we can take the square root of, and then that will leave me with an x to the 1st here. Now the y to the 4th we can definitely take the square root of, and then that doesn't leave me with any y's over here. So now I take the square root of 49, I get 7. The square root of x to the 8th is x to the 4th. The square root of y to the 4th is y squared, and I'll leave the 3x. So there it is, all completely simplified. Again, one of the real keys here is that we can take the square root of any even power, but the odd powers are kind of more obnoxious. So we find the largest even power that's less than whatever our odd power is. So if I've got x to the 9th, I can definitely take the square root of x to the 8th. Okay. Now, let's take it up a notch, simplifying higher order roots. Now, we're going to work on more of these in our next lesson as well, but we want to kind of get started on them. We can extend the simplifying process to include cubed roots and higher order roots by simply extending our thinking. Right? Now, what can be a little bit tricky about this is, of course, as soon as you get by square roots, once you deal with cubed roots and 4th roots and 5th roots, now you're thinking about cubing numbers, raising numbers to the 4th, raising numbers to the 5th, etc. Let's start off kind of easy in exercise number 7. Simplify each of the following higher order roots. Letter A, the cubed root of 16. All right, now we're going to do the cubed root of 16 very similar to what we would have done before. Let me kind of just write that down. But I want to think about perfect cubes now instead of perfect squares. So perfect cubes, right? Maybe just side of my paper here, I've got 1 cubed, which is 1, 2 cubed, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125, etc. And then I wrote down 126. I said 125 though. But then I wrote down 126. So I was already thinking about what 6 cubed was, which was 216. Anyway, right, so now I'm kind of looking at all of these numbers and thinking about what is the biggest one that divides into 16. That's pretty easy. It's equal to 8. So now I can take the cubed root of 16 and break this into the cubed root of 8 times the cubed root of 2. Maybe make that look like a multiplication symbol. The cubed root of 8 is 2, and the cubed root of 2 I have to just leave like this. So the cubed root of 16 is 2 times the cubed root of 2. All right, great. Why don't you take a shot at letter B, where we're trying to simplify the cubed root of 108. All right, so yet again, what we want to be thinking about is which one of these numbers will easily divide into 108, all right? And just playing around on it, we can find out that 27 goes into 108, and it goes into 108 4 times, okay? So 27 divides into 108 4 times. And you, again, just sit there on your calculator, what's 108 divided by, etc. So what I'm going to do is I'm going to write this down as the cubed root of 27 times the cubed root of 4. 4 times 27 is 108. The cubed root of 27 is 3. And the cubed root of 4, I simply have to leave as is. I think that the cubed root of 250, right, is actually kind of a little bit easier because it's pretty obvious to me that 125 divides into 250. So pause the video now and see if you can simplify the cubed root of 250. All right, well, 250 is obviously 2 times 125. So I'll make this into the cubed root of 125 times the cubed root of 2. Cubed root of 125 is 5. So I have 5 times the cubed root of 2. All right, now we get to one that finally has a variable underneath it. Now, again, I want you to think about finding cubed roots of things raised to powers, okay? So what should be obvious, and maybe just kind of, we'll talk about this down here a little bit, is that, you know, the cubed root of x cubed is x. That's simple enough, right? But if I took something like x squared times x squared times x squared, I'd have x to the 6th, right? So the cubed root of x to the 6th is x squared. All right. More importantly though, right, the cubed root of x to the 6th is equal to x to the 6th to the 1/3, and 6 times 1/3 is 2. So I'm going to be able to take the cubed root of any quantity raised to a power that's divisible by 3, right? Just like I could take the square root of any quantity raised to a power that was even, right, that was divisible by 2, the cubed root I can take of any quantity raised to a power that's divisible by 3, right? Hopefully that makes sense. So let's take a look now, we'll eventually erase all that, at letter D. Letter D, we have the cubed root of 128 times x to the 8th, right? So the first thing that you do is you say, all right, well, which one of these numbers divides 128 nicely? Okay, and that hopefully will be pretty obvious. Then you look at x to the 8th and you say, well, what is the largest power that is less than 8 that is divisible by 3? Okay? And that you'll be able to take an easy cubed root of. So let's do this together. All right, we can find the cubed root. Oh man, now I don't have very much room, and I can't really write all that small, but we'll try to get it in here. Oh, boy, one more time. The cubed root of 64 x to the 6th times the cubed root of 2 x to the 2nd. Now let's talk about this a little bit, right? We can find the cubed root of 64, it's going to be 4. We can find the cubed root of x to the 6th, it's going to be x squared. I know it's kind of hidden down here a little bit. Let me bring it up just a bit, right? There it is, right? The cubed root of x to the 6th is going to be x squared. But we can't find the cubed root of 2, and we can't find the cubed root of x to the second. So all of this then just becomes 4x squared times the cubed root of 2x squared. And let's try to make that look a little bit more like a 2. All right. And that's it. And we can just keep extending this to higher powers, larger powers, things like that. And what, of course, becomes more and more difficult as we go isn't particularly the exponents on the numbers. It's things like, well, what is a perfect fourth? What's a perfect fifth, etc., like that, right? So, when we're looking at something like the fourth root of 162, so let's take a look at letter E, right? We're trying to simplify the fourth root of 162. Well, then, right, we want to start thinking about things like, well, 2 to the fourth. Well, that's 2 times 2 times 2, that's 16. And 3 to the fourth, that's 81. And 4 to the fourth, that's 256. And again, we might need to even do those on our calculator. But right away, it's not going to be the 256. And what we can definitely see, right, is that we can see that 81 divides nicely into 162. So what we can say is that the fourth root of 162 will be the same as the fourth root of 81 times the fourth root of 2. The fourth root of 81 is 3. So we can make this into 3 times the fourth root of 2. Yes, just what I always wanted. I wanted to know that the fourth root of 162 can be rewritten equivalently like this. You might say that I have a disdain for these types of problems, and I kind of do, because I really don't see the point of them. But I guess it's good to just understand the nature of roots and how one can simplify them, I guess. All right, why don't you take a look at letter F and see if you can use what we've already seen with cubed roots and square roots to try to figure out how to simplify the fourth root of 16x to the 8th. Pause the video now and see what you can do. All right, well, great. So what can we do on this? Well, one of the things that's cool, right, is that we can find the fourth root of 16. The other thing that's kind of cool, and let me write this a little bit bigger, we've got the fourth root of 16x to the 8th. Just like cubed roots have to have a power divisible by 3, and square roots have to have a power divisible by 2, fourth roots, if we want to take a fourth root of some variable raised to a power, we just need that power divisible by 2. So we don't break this up at all. The fourth root of 16 is equal to 2, and the fourth root of x to the 8th is equal to x squared. So that simplifies all the way down, 2x squared. All right, not much that we have to do there at all. So maybe let's do a little bit more of a challenging one in letter G. Let's take a look at that. We've got the fourth root of 48x to the 10th, y to the 5th. All right, so this one you got to do a little bit more work on. Think about the 48, think about the x to the 10th, think about the y to the 5th, and see if you can simplify those. All right, well, first things first, the 48, 16 divides into it nicely. So we're going to have the fourth root times the fourth root. All right, here we'll have 16 and we'll have 3. Then we think about the x to the 10th. Well, I can definitely take the fourth root of x to the 8th. That'll leave me with an x squared over here. And then I can certainly take the fourth root of y to the 4th, and that'll leave me with a y to the 1st over here. So now the fourth root of 16 is 2. The fourth root of x to the 8th is x squared. The fourth root of y to the 4th is as easy as it gets. It's just y. And then all the remaining things we have to leave under the fourth root symbol. And we get 2x squared y times the fourth root of 3x squared y to the 1st. Okay, one more problem, then we'll wrap this up. Let's take a look at letter H. Here we have the fifth root of 64x to the 12th, y to the 15th. Wow, okay. Well, we got to do this dance again. And actually what I think I'm going to do is give myself plenty of room. We'll just rewrite the problem down here. So let me just kind of like put it down here. We've got letter H. We're looking to simplify the fifth root of 64 x to the 12th y to the 15th. Now, the hardest part of this one is dealing again with the 64 because we have to find the largest perfect fifth power that goes into 64, right? And again, move our little hypercube out of the way. We would have 2 to the 5th, which is 32, 3 to the 5th, which is 200, and let's see, we got 81 times 3 is 243, and I'm not going to even go on, right? As soon as I get a number that's bigger than 64, forget about it, and honestly, it's the 32, right? 32 goes into 64 2 times. Now, of course, we want the biggest power that is divisible by 5. So, pause the video now and see if you can simplify this last problem. All right, here we go. So, let's write this as the fifth root of 32. Now, I'm going to write that as x to the 10th, and the 15 is already divisible by 5. So, y to the 15th times the fifth root of 2 times x squared, and the y is already all in the other location. So now the fifth root of 32 is 2. The fifth root of x to the 10th is x squared. The fifth root of y to the 15th is y cubed. And we've got to leave everything else. All right. Awesome. That's it. Simplifying roots. Simplifying roots, whether they're square roots, cube roots, fourth roots, fifth roots, or any higher level root, and my goodness, I hope you never have to go higher than a fifth root, means to find the square root, cube root, or whatever of everything you can, and then leave what you can't. Part of that is numerical, right? Taking whatever numerical coefficient you have and finding the biggest perfect square, the biggest perfect cube, the biggest perfect fourth power, fifth power, etc. that divides into that number. So 32 is a perfect fifth power, so I break 64 into 32 times 2. Ironically, the variables are almost easier to deal with, right? Because they're all about divisibility, right? So I can't divide 12 by 5, but I can divide 10 by 5. So I break x to the 12th into x to the 10th times x squared. But y to the 15th I can divide by 5, so I can find the fifth root of y to the 15th. It's y cubed. Think about it. Y cubed raised to the 5th is y to the 3 times 5 is y to the 15th. So all we want to do when we simplify a root is take the root of what I can and leave what I can't in terms of a product. All right, let's wrap this up. That was a lot in that last problem. Okay, so today we revisited certain things that we knew about fractional exponents, how they connect to roots, and then through that connection between fractional exponents and roots, we also explored how you can, quote, simplify roots, right? And we just beat that one quite a bit, so we're not going to keep playing that song over and over again. We're going to be using fractional exponents a lot throughout this unit, and really we're going to be playing around a lot with different things that involve square roots, cube roots, fourth roots, etc. So you want to make sure that you kind of understand all of this, especially the equivalence between fractional exponents and roots, but also in a certain sense you do have to know how to simplify roots, if for no other reason than getting that multiple choice problem correct on that standardized exam. All right. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.